So this is Unit 1, Lesson 12 for our AP Calculus course. The unit is called Limits and Continuity. The lesson is called Defining Continuity at a Point. What we're going to learn in this lesson is how limits help us formally define what it means for a function to be continuous at a specific point. A function f is continuous. So here's the definition, the formal one. A function is continuous if the limit as x approaches some value a is equal to f of a. So this definition, if we unpack it a little bit, there's kind of three things we have to look at. One, f of a is defined. And so if we have on our graph some function at x equals a, there's some kind of definition, a dot, a line, something. Two, we need to know that the limit as x approaches a does exist. And so what that means is the limit as x approaches a from the left is equal to the limit as x approaches a from the right. So on this graph, as x approaches a from the left, we're going up to the same point as we approach a from the right goes down to the same point. So we have the same limits. But also, and third, and this is also equally important, the limit as x approaches a of f of x has to also be equal to f of a. And so that basically this dot has to be right on top of the line. Can't be below it, can't be above it. And so if we combine idea number 2 and 3, then we could say the limit as x approaches a from the left has to be equal to, not only does it have to be equal to the limit as x approaches a from the right, but it also has to be equal to f of a. So all three of these have to be equal. A very informal definition for continuity, and this is kind of how it first made sense to me when I was taking AP as a high schooler. If you could draw the graph of the function without lifting your pencil, then the function is continuous. So if I reach a hole in my graph, I have to lift my pencil over the hole. Even though it's an infinitesimally small lift, I still have to do it. Or if it's jump or infinite discontinuity, I'd have to pick up my pencil to continue the line. So picking up your pencil to draw the function is basically means there's a discontinuity there. So that's that. Both formal and informal definition. So let's look at an example here. So if f is defined below, what value of k is f continuous at x of 3? So if we apply it, what we need to know about continuity, we need to know, is a defined? At this point, yes, it's defined as some k value. And so we'll replace k with some number at the end. And yes, the answer is 2. Number 2, does the limit as x approaches a from the left and the right, are they equal to each other? Well, we take a look at that. So if we do direct substitution for this limit of this function, when x is not 3, we get 0 over 0 indeterminate form. Plug in 3 for x on top and bottom, we get 0 over 0 as a determinant. So we could factor the top and bottom polynomials, and we see that we have x minus 3 on top and bottom. And so if we cancel that out, and again, this is very technical, what I'm about to say answers why there's an equal sign here, but there is not an equal sign right here. And notice it is very important that there's not an equal sign right here. And the reason that is because if we cancel out x minus 3 from our denominator, what we're doing is we're removing a hole at x equals 3. So the difference between this function and this function is that this function doesn't have a hole at 3. So to say that the limit as x approaches 3 of this function is equal to this function, we have to specify that x cannot be 3. So it's equal to this one. It's not the same function as this one, because if we just get rid of that restriction, then they're no longer the same function. But the limits will still be the same. And so I just want to pound that fact that there's not an equal sign here, sort of pound that domain restriction in there to your brain so you know and you don't make that mistake. A lot of AP testers will hit you or dingy points for putting an equal sign right here. Okay, so that side tangent out of the way, let's get back to here. So we crossed off x minus 3 from top and bottom, and so now we can do direct substitution for this function. If x equals 3, we have 6 on top, 3 on bottom. So the limit as x approaches 3 is 2. And so to answer our question, yes, the limit as x approaches a does exist. And now we want the limit to equal f of a. Well, if the limit approaches 2, then at x equals 3, we want it to also equal 2. So k is going to have to be 2 to make this graph continuous. And so basically the point 3, 2 is the dot that plugs the hole on our graph. So we have removable discontinuity. 3, 2 plugs the hole. So 2 would be the best answer for this one. Here's what the graph of that looks like. So we have f of x equals our function for all values except for 3. And if we check, we have a hole at x equals 3. I could type in f of 3 and we see that it is undefined. Desmos is notorious for not showing holes on their graph. So it's really hard to hit this thing right on. I think I just hit it just now, but the easier way to do it is just type in f of 3 because we already have f defined. We see that it's got a hole, it's undefined. And so if we add the 0.32, that fills the hole, and we now have a continuous function. All right, another example. So this is one that we can't solve by factoring. Let f be the function defined below. For what value of k is f continuous at x equals 0? So our definition, first of all, is f of a defined? Does the limit exist? And does the limit equal f of a? So f of a is defined so far as it equals k. F of 3 equals k. Oops, sorry, wrong one. F of 0 equals k. Does the limit exist? So now that's the tough part here. So we're going to find the limit as x approaches 0 for this function up here. If we do direct substitution, we get 0 over 0 indeterminate form. So what we're going to do to simplify this fraction is we're going to multiply by the conjugate of the numerator. So the numerator is the square root of 7 minus 2x minus the square root of 7. So the conjugate of this would be the same thing, but you swap this minus sign out with a plus sign. So square root of 7 minus 2x plus the square root of 7. We're going to multiply the top and the bottom by that same conjugate. On top, conjugates give us difference of squares. So the first thing squared minus the second term squared would be 7 minus 2x minus, and the square root of 7 times the square root of 7 is just 7. And so we can see we have 7 minus 7 in the numerator that cancel out. The bottom, I'm not even going to worry about multiplying this x into this grouping because I see that I have x on top and bottom left behind. And so those x's will cancel out. And we're left with negative 2 over our conjugate. Notice we skipped one equal sign on this problem as well. And so the reason that is because when I multiplied by the conjugate, we're changing some of the holes here. So for this specific example, we don't really need to specify that x can equal 0 because we still have x here. But in the next line, we don't say equals because we're getting rid of the x. And so because the x is gone, the first function and the second function are no longer equal because this function is defined at 0 and this function is not defined at 0. Even though they're not equal, the limits will still be equal. And so we can do direct substitution for this one. If we do that, we plug in 0 for x. And the only spot that remains for x, the numerator stays negative 2. The denominator simplifies to 2 root 7. We cancel out a 2 from top and bottom. We get negative 1 over root 7 as our simplified answer. So A would be correct. Before I jump the gun and answer that, though, we would say our definition was A is defined, check. The limit as x approaches a exists. Check. The limit is negative 1 over square root of 7. And now I want to show that the limit is equal to f of a, which we're going to define because it's defined as k right now. So jumping back to this problem, if we define k as negative 1 over square root of 7, then we have effectively plugged the hole and made our graph continuous. So we've done our due diligence. The answer is A. Here's the graph, what that looks like. Again, I can type in f of 0 and see that it is undefined. We have a hole, and so we can plug in that point to fill the hole. All right, here's a similar to how you see it on the homework set. It's a little bit trickier to consider the fact that we have a k for both parts of our function. And so if we stick with our definition for continuity, then this is going to be pretty straightforward. So does the limit as h, well, first of all, h of 2 or negative 2, does h of negative 2 exist? And because we have a greater than or equals to sign here, because it's equals to, then h is defined at negative 2 by the top function. And now the limit as x approaches a from the left and the right have to be equal. And so because k is in both of them, we're basically at this step trying to figure out what k is by saying that the left bound and the right bound limits have to be equal. So if the right bound and the left bound are equal, well, the right bound is when x is greater than negative 2, so we use kx squared for the right bound. And the left bound is when x is less than negative 2, so we use kx minus 12 for the left bound. We'll just substitute those expressions in for the limit functions. So now we get kx squared has to be equal to kx minus 12. So that's kind of tricky to solve because we have two variables and two equations. We don't really have enough information to pinpoint k at this point. So what we have to do is go back to our definition of continuity. And the third point is that the limit has to be equal to that value for h itself. And so because we're looking at the limit as x approaches negative 2, we want to say h of negative 2 is also equal to that limit. And so for that reason, we could just plug in a for x, or in this case, negative 2 for x. And so if we do that, that makes this a whole lot simpler. So it'd be k times negative 2 squared is equal to k times negative 2 minus 12. And then we just have a simple, one variable linear equation in terms of k, and we can solve that for k equals negative 2. So if I plug in negative 2 for k, then the limit on the left and the limit on the right are equal, but also they're continuous from one to the next. So for that to be true, for continuity, or for h to be continuous at x equals negative 2, we got to use negative 2 for our k value as well. So if we took these two functions, we put them on a graph, and we used kx squared only to the right of negative 2, and we used kx minus 12 only to the left of negative 2, we would get this graph right here. So notice when I write the function in, I just use f of x for the right bound and g of x for the left bound. I also use this bracket notation. I call them mustaches because it makes me happy. But this is our domain restriction. So here's how we say x has to be greater than or equal to negative 2, which cuts off our graph at negative 2 and only goes to the right. If I get rid of that domain restriction, then we get the whole red line, not just the part that we want. So I'm going to put that restriction back in. Similarly, for g of x, our left bound, we have a domain restriction. X is less than negative 2. And now currently k is set to 0. So if k is 0, here's what the left and the right look like. Definitely jump discontinuity. Now if we change k, we can watch the graph change. I'm going to turn this, make it a little easier to see. We can watch k change. Boom, boom, boom. And if k is a negative number, they get closer. And it looks like graphically they connect when k is... Ooh, this glitches. Let's just type it in. Oh, come on, cursor. There you go. We know the answer is k is negative 2. So if I just type in negative 2, I see that my left bound and my right bound both meet up. And so we now have, if k is negative 2, then our graph is continuous over the whole function, which is fun. All right, so here's our trig flex for this lesson. And this is kind of, well, I don't know. I think this is kind of a very rigorous problem. There are some similar AP questions that look kind of like it. So I just want to show it to you, expose you to it so you know it exists. And it's based off of two common trig limits. So here's two things that we're just gonna spend some time with these two equations or functions. Look at them graphically. Look at sine of x over x. You can visually see that the limit as x approaches 0, our function approaches 1. And for the second one, if you graph this, you can clearly see the limit as x approaches 0 is 0. Looking at the equations is not intuitive, but if you graph those, it is very intuitive that these are true. And so these are just two limits with trigs that we just want to know. So make sure you know those. So our question is, what value of k would make our function continuous at negative 2 or positive 2? When x is not 2, we have our function defined by this trig function, and when x is 2, it's just k. So if we follow our definition for continuity, does h of 2 exist? Yes, it does at k. Does the limit from the left and the right exist? That's where all of our work's going to come into play. And then 3, does it equal to f or h of a? And so in this case, like before, if we find the limit, then that's the value we want to plug in for k to make h of 2 equal to the limit. So let's, conceptually, that's what's going on here. But the hard work comes in, how do we find the limit of this function right here? So if we just look at that limit as x approaches 2 for 3x minus 6 times cotangent of x minus 2. Before we beat our head into the wall, we could do direct substitution. We get 0, sorry, we get 0 here. And cotangent, I know, is cosine over sine. And so if I plug in 2 for x, we have cosine of x minus 2 over sine of x minus 2. That would be 1 over 0, which is undefined. So we have 0 times 1 over 0, which is the same thing as 0 over 0, because you can't divide by 0. It's indeterminate. So that's, yeah. So like I said, don't beat your head into a wall. What we're going to do is we're going to turn this cotangent into cosine over sine. And then we're going to grab this first trig limit that we're going to pound into our heads and not forget. And we're going to make this limit look like something similar to what we have over here. So we're just going to do some trig identity manipulation to make this work. So first off, in the green, we're going to make this thing look like, well, this step right here. So take cotangent is cosine over sine. We have our binomial times cosine divided by sine. I'm going to rearrange the multiplication and the division here, which is totally fair game. I'm going to put the 3 up front. I'm going to take x minus 2, divide it by sine, and then multiply by cosine last. So we break our function into 3 products. Now, one of our rules, we have the limit as x approaches 2 of a function times a function times a function technically. So one of our definition of limits, we can break that into 3 different limits. So the limit as x approaches 2 of 3, the limit as x approaches 2 of x minus 2 over sine of x minus 2, and the limit as x approaches 2 of cosine of x minus 2. So the first limit and the third limit are pretty straightforward. So limit as x approaches 2 of 3 is just 3. The limit as x approaches 2 of cosine of x minus 2. If we direct substitute 2 in for x, we get cosine of 0, which is 1. So that kind of simplifies things, but doesn't tell us the middle piece. The limit as x approaches 2 of x minus 2 over sine of x minus 2. And so that's where this identity comes into play. So we're going to make this trig identity look like this right here, with x approaching 2 and with x minus 2 on top instead of x on bottom, and sine of x minus 2 on bottom instead of sine of x on top. So we're gonna make this look like this. The first step is we're going to take this limit function and we're going to write the reciprocal. So we can split up division just like we can multiplication. So we think of the limit as x approaches 0 as a function over a function equals 1, which we could write as a fraction of 1 over 1. And the reason why I want to think of this as 1 over 1 is because I can flip or write the reciprocal of our functions, and it would be equal to the reciprocal of the limit. That sounds crazy, and we can explain that in terms of our function composition for limits a few lessons ago. I would suggest if that doesn't sound familiar to you, go back and check out our properties, our algebraic properties of limits. So we could say that the limit as x approaches 0 of x over sine of x would be equal to the reciprocal of 1, which is 1 over 1 would still be 1 over 1, which is still 1. So we can say this step right here. Now, we can change our input from x to being x minus 2. So if we change this to x, then in our function x becomes x minus 2 in both places. So we say the limit as x approaches, or x minus 2 approaches 0 of x minus 2 over sine of x minus 2 is still equal to 1. We've just tweaked our function yet again. And now if x minus 2 is approaching 0, then x is approaching 2. And we're not doing anything crazy here. Just consider a value of x. If x is 10, for example, or actually that doesn't make sense. Let's say 2. X is 2, for example. 2 minus 2 is approaching 0, right? So if 2 minus 2 is approaching 0, then x, 2, would be approaching 2. So that's just kind of some simple math right there. So we could say that since the limit as x minus 2 is approaching 0 of this function equals 1, then the limit as x itself is approaching 2 of the same function is still equal to 1. Phew, we did it. Notice this function, this limit function, looks just like what we have right here in our problem. We have limit as x approaches 2 of x minus 2 over sine of x minus 2. So now we've shown that this whole thing equals 1. And so good riddance to this thing. Sine of x, fraction, limits, blah. Anyways, so we have 3 times 1 times 1. So our limit as x approaches 2 of this function is 3. So that was a really long, nasty thing. So let's go back and take a 10,000 foot view of what we were talking about here. We want to find a value for k that makes this function continuous. So basically, we want the limit of this function to be equal to k. In other words, what value of k would make this a point that fills the hole? So since the limit of our function as x approaches 2 is 3, limit is 3, then we want our x value equals 2 to be defined as 3. So h of 2 needs to be 3 to plug this hole. So the point 2, 3 would plug the hole because 3 is the limit. And so 3 is our best answer. It's the number we want to plug in for k to get rid of our removable discontinuity. And there's our trig flex for the day. Yeah, I'll leave that at that. Here's the graph for this function. We see 3x minus 6 times cotangent of x minus 6 looks pretty fun. We've got an upside down u and then a bunch of lines. If you zoom out, you see that's only one u in this thing. And there's a bunch of lines. Forever and ever. It's kind of crazy. Crazy just like calculus. Anyways, we do see that at 2, we have a hole. And if we put the point 2, 3 in, it's going to fill our hole. Takeaways. We can apply the definition of continuity at a point to ensure a function is continuous. And again, our definition of continuity is the limit has to be equal to f of a, or the right bound limit and the left bound limit have to be equal to each other, as well as equal to f of a. We've done we're working on continuity, but we can see that our definitions of continuity are completely dependent on the concept of limits and our limit function. We also need to know that cotangent is equal to cosine over sine. It's very important. And we also need these two trig limits. If you memorize two trig limits, these are the two you'd want to memorize. And when I say you want to memorize, I mean like for an AP test. So that's that.